see in this image how the water is squeezed through here. And that increases the velocity of the current called the Antarctic circumpolar current that goes through here. And in doing so, that makes that current the strongest on Earth. It does the same thing with winds. So now you have a perfect storm, and the Drake Passage goes by two monikers, the Drake Lake and the Drake Shake. And you can imagine Drake Shake is very stormy. And it turns out this has the stormiest weather for the whole Earth. And we went there in January, and yet we had waves that were 35, 40 feet. And January, the part that we did was supposed to be the calmest time. So now I'm going to go into several sets of images here. And we're in the ablation zone. And all glaciers, as you know, have two major zones, the accumulation zone and ablation zone. And what results in the ablation zone are icebergs. And you see quite a few of these, varied in size and shapes. And then the question is, why do we get icebergs? I mean, it's intuitively obvious that they're here. And so we want to discuss that a little bit. And you can see in these three images here, one of the reasons that we have icebergs, and those are the crevasses. So you can see a plethora of crevasses in each of these. And these are the natural breaks in the ice when it moves over uneven topography, which then creates uneven stress on the ice, which then results in the crevasses. And some of these can go down 160 feet deep, and they can be 70 feet wide. And these are very dangerous for people trying to cross a glacier because snow makes snow bridges over them, and those snow bridges are weak and people will fall in. And be assured, if you fall on glacial ice, it's the same as falling on rock. So imagine falling 160 feet on rock. So these crevasses move with the glacier down to the water's edge. And then they encounter the upper buoyancy of the water, so that's a new force on it. And all this is taking place under the pull of gravity. Now, since we're talking about icebergs, keep in mind that 1/10 of the iceberg is above water, 9/10 is below the water. And so I'm going to be using what I call the 9/10 rule at different times. And so in these images, I have several arrows. And here's one of our guides in a zodiac. Here's a penguin, and then a bunch of us in a zodiac, and then another zodiac. You could use any of those as an object of scale, and you could estimate then how high an iceberg is above the waterline. So hypothetically, let's say an iceberg is 100 feet above the waterline and apply the 9/10 rule, then the vertical dimension of that iceberg is 1,000 feet. And we're going to see coming up an iceberg called A23A, which was 1,320 feet in total thickness. So these things can be massive. So now we're going to go to another set of images and get a little bit into natural history. And Antarctica has 7 types of penguins. We're only going to talk about 4. We only saw 4. And the first one is the Gen 2 penguin. You can see the spelling here. And they're characterized by having a solid white abdomen. So here's solid white abdomen, solid white abdomen. And here, this one is making a trumpeting call, which is this mating call. And I don't know how they do it, but they can distinguish one mating call from another. And that's simply amazing. Now, this is an iceberg. And if you've ever been into an ice cave that's in a glacier, you'll know that it has a bluish color to it. And they're just beautiful. Well, since icebergs are derived from the glacier, then the same thing happens here. And almost all glaciers and icebergs are white on the surface and blue internally. I'm going to explain that a little bit later. I'm just introducing it now. Over here is a leopard seal. Cute as they may be, these are apex predators. These can be 11.5 feet in length. They can weigh 1,300 pounds, and they've been known to kill people. And therein lies a story that I'll tell you a little bit later. And down here is a southern giant petrel, one of the indigenous birds to the area. And these and another bird called skua, S-K-U-A, which you're going to see pictures of, fly into the rookeries of the penguins and peck the eyes out of the baby penguins and kill them. So that's part of nature. In the background is an out of focus Roche-Montagne. You're going to see it in much better focus a little bit later. And I'm sure you're familiar with Roche-Montagnais. So here is a iceberg, and here is the glacier down at the water's edge. Let's take this one first. We can see two ice caves or sea caves forming in it. And when I began to look at the icebergs, I was wondering, are all their shapes and all their features random, arbitrary, or can we look at some factors that maybe help explain their occurrence? And so I think here, this developed along a fracture coming down that may be part of a crevasse. You can see the crevasses. I said that they can extend 160 feet deep. And when water splashes into a crack, it freezes with pressure in excess of 6 tons per square inch. And we know it's capable of breaking up the ice in the same way that it broke up rock under periglacial conditions to form our boulder fields and our scree slopes in central Pennsylvania. So it's very powerful. This other sea cave, from this perspective, I cannot tell. I just am guessing that there's a fracture around the corner coming down, maybe in this direction. Anyways, up here, we have what I'm calling incipient sea caves. And these are probably random from the wave action. Over here is a second penguin type. And this also has a solid white abdomen, but notice it has this black stripe along the chin, hence the name chinstrap penguin. And when you see a bevy of them, I mean, it's hilarious because they all look like they have a smile on their face. Can you see this? Doesn't that look like a smile on his face? And it's interesting because then you'll see a whole bunch of them and everyone has a smile. This is beyond cute, just feeding his chick. Now we get into some shapes of icebergs. And I come back to what I said before, and I'm going to provide some insight into this. I think there are some structural controls that help make these shapes. So let's look up here and we see stratification, and these are the original snow accumulation lines, and ice coring goes through these to get the isotopes of oxygen O16 and O18 to give us paleo temperatures. But notice over here we can see some fractures. So these are structural controls on some of these shapes. And here we can see a flat surface. Down here we see a flat plane, and this must have been some discontinuity, and then it all dropped off. Now I have two names up here, Bergibits, and down here growlers. There are strict definitions for them, and for this talk I could care less about that. I'm going to just summarize in essence of time and say medium size are Bergibits. They're all icebergs, and the smaller ones are growlers. So let me explain how the name came from growlers. The gases that are in them when they escape make a growling noise, so hence the name growlers. Bergibits, here's the name icebergs. If you chop off the word ice and remove the S and add a Y, you get Bergy, and these are bits of the original icebergs. That's supposedly, and I looked it up, the derivation of that name. Over here is a fur seal pup, one of the indigenous mammals that are down there. This is that South Georgia island at a place called Grytviken, and it used to be a whaling station. We hiked up here, and South Georgia happens to be the graveyard for most of the icebergs coming out of the northwest quadrant of Antarctica. And this image, which I think is picturesque, shows that quite well. Lots of icebergs. And then we have the unusual green iceberg. We only saw two of them. And that should excite you a little bit because, they're pretty darn unusual. I want to talk about the origin of this a little bit later. So I'm just whetting the appetite now. So now we have a third type of penguin called the king penguins. And like the king in the deck of cards, which is always colorful because it's the king, here we have these brilliant colors of orange and yellow, and these are the king penguins. And here's a bevy of them in front of two elephant seals. Now, these are behemoths, and these are males. These are the beach masters, and these things can weigh 8,800 pounds, but they can dive down over a mile in the ocean. You wouldn't want to get trapped in one of these because, as I said, these things just weigh multiple tons. Well, they ignored us, so that was fortunate. Another fur seal in the snow, another iceberg with those different colors, which I'm going to explain, a Gen 2 penguin, solid white abdomen, and just terrific swimmers can go 23, 24 mile per hour in the water. And here it has leaped out. And now the last image in this group is a panorama. It shows the ice has come down to the water's edge where we're in the ablation zone forming icebergs. And so we can use these terms, Bergia bits for the medium-sized ones, growlers for the small ones. In the background are nunataks, and in the foreground is a Gen 2 penguin, solid white abdomen, Gen 2 penguin rookery that extends around here. And if you look carefully, you can see these mounds. These are the nests. You can see some of the penguins sitting on the nest. And the male goes down along the beach, usually a shingle beach, and picks up pebbles and makes the nest for the female, and then they share the duties. And this is this is just spectacular scenery. So this is a special place, and some of that designation was afforded by protections in 1959 through the UN, but notice they expire in 2048. And I'm going to show you very shortly some threats to these protections. And these are some of the articles. I wouldn't dare read these all to you. I'm going to paraphrase the two in red, and I want you to hold these thoughts. Peaceful purposes only, and no territorial claims, okay? I'll repeat that. Peaceful purposes only, and no territorial claims. Now, I'm using this outfit's one image, and I don't care about them, but I'm going to give them credit. If you have $20,000 a week to spend, you can stay in their luxury huts. We didn't do that, by the way. But here, this image that they had on the website shows three geological features very, very well. And the one that's nearly ubiquitous is, of course, the Continental Glacier. So everything underneath the ice is glacier. Background is Nunatak, and here we have a beautiful roche montagnais. You can see the Stowe side, the lee side, so the glacier moved from left to right. Now over here, and you can read this on your own, but you can see the number of visitors that went to Antarctica and in that season, and some people would quickly jump on the bandwagon and say any degradation that's taken place in Antarctica is due to the tourist season. We should ban that. And I disagree. And it turns out, if you go to a Scientific American article in 2023, it discussed that very issue. Antarctic research stations polluted a pristine wilderness. Imagine in the first decade of their existence, these research stations, they were permitted to pump or pipe untreated human waste out in the Antarctic Ocean. And that went on for a decade. And these are the primary source of degradation on the continent. They've leaked chemicals into the ground, and you can see some of the trash that accrues. I just think, it's just my opinion, I think they should keep a more pristine setting. That's just me. So here are some headlines from last year, and these are the threats to the protections. And I want to just read through these very quickly. So Russia makes a move on Antarctica's oil. And that's in contradistinction to what the USGS said in 1983, but I think this is more update. Can you imagine the technical difficulty if this was on site and drilling through 12,000 feet of glacier to get to the oil and keeping that hole open? Consider alternatively if they're having drilling platforms off the coast and these huge icebergs come by. And now I want to tell you a little bit about A23 in regard to being a huge iceberg. It weighs, or did weigh, 1 trillion tons. And then I'm repeating myself, its thickness was 1,320 feet. Yeah, you just can't move that. Second headline, China and Russia block protections. That's unfortunate. And then this is rather disconcerting. I don't think this will ever be allowed, but these were the claims. Iran claims Antarctica and plan to carry out military and scientific work there. So those are some of the challenges. For us, we had these biosecurity measures, and they could have had more. I applauded every one of these. And when we were going ashore and coming back, we had to walk through vats of disinfectant. We were ashore, we couldn't sit down, couldn't put our packs down. And when we came back, our boots were power washed. In the Falklands, we had a government inspector inspect us. And we were back on shore, Velcro zippers and packs were vacuumed. And this was the limit of people at any one time. and I think this was fantastic. And it's, to me, it's like going to our national parks. You should be allowed to visit, but you need to have great conservation. So now I'm going to go back to Ushuaia because during the Pleistocene Ice Age, it was completely covered by glaciers. We want to look at some of those. I know it's a review for everybody, but review doesn't hurt anyone. So bear with me. And the city is very attractive, about 70,000 people. In the background, you can see a U-shaped, very typical U-shaped glacial valley, a cirque. Now, I have found from my own experiences, when I look at cirques from a distance, they are misleading to me. And I would approximate how high the cirque walls are, and I'd say 150, 200 feet. And then I hike a couple of miles to get to them, and I walk into them, and these walls can be many times higher than that. And in fact, some cirque walls can go up 1,000 feet. So there's certainly been a lot of plucking action going on with the glacier. Down here is another U-shaped valley / hanging valley because the ocean's far below the city. Well, not far below, but below it. And just another one that you can look at. Now we come back to the Roche-Montagne that I showed you when I also showed the southern giant petrel. But here it's in focus now. We can see the Stowe side, the lee sides of the glacier moved from left to right. I think from the distance that we were, that this red arrow is pointing to glacial grooves. And everyone knows that that's due to rocks being on the other side of the glacier and scouring the rocks. Now, this is wonderful habitat, and you can see some seals up here and here, and I can tell you there's just a plethora of birds up here. It was just a whole bunch of them. So while in Ushuaia, we stayed in a hotel until our ship was cleaned up to receive us, and I saw in their walkways these beautiful fossils, some of which were 6 inches in dimension. They certainly caught my attention. So I took a stab at identifying them, but before we go there, let's look at some stylites. There's one here, and these are symmetrical stylites. And you find them, of course, in the carbonates, which would be limestone, dolomite, and marble, but you also find them in sandstones if they have carbonate cement. So now back to the fossils. Here we have a belemnite rostrum with this fossil range. So that put a constraint on possible identifications of these coiled fossils. And none of them are gastropods. This is just poor preservation. So I began to think, well, maybe we have a gonatitic ammonite, and that didn't make sense because that was in conflict with the belemnite. So here are my possibilities, and I stand corrected if anyone wants to offer a better opinion. And I think that what we're seeing, at least on this one, is a ceratitic ammonite, but it could be an ammonite, but I don't think it is, which is shown here. And here's your ceratitic ammonite. Or if I wanted to cop out, I could just say poorly preserved ammonites. That's a real cop out. This fossil, and again, some of these were 6 inches in dimension. I didn't have a scale, and I apologize. The best I can come up with is this is a truncated echinoid. Possibly, it could be a barnacle that's been truncated, but it seemed a little large for a barnacle. So that's that. But behind the hotel, we did a hike that took us to a peat bog. And everyone can read this. You know that peat is the first stage of coal. And what's interesting is that most of the peat around the world is of the same age, dating to about 12,000, 11,000 years ago, which is at the end of the Ice Age, when many areas were supersaturated. And if you have sphagnum moss, or if you have conifers, then you'll get tannic acid, which gives you this color, and that kills the bacteria that normally would decompose the vegetation, and the result is peat bog. Now here's another U-shaped glacial valley. You can see this is one, but it's obscured with the tree. As I said, Ushuaia was completely covered with glaciers. Now, 2 images of the same thing. This is the ice over Antarctica that's intact. Here it's been digitally removed. Now you can see why there are crevasses in the ice. Look at how uneven the topography is and the uneven stresses that would be put on the ice. So let's look at some features up here. The Transantarctic Mountains, you can see them in both of these images. And this is Mount Everest, which was down here someplace, and I'm going to come to that next. And that's the active volcano. We can see a few nunataks. I want to make sure you see these ice shelves. We're going to see an image later, and we have ice shelves on the back side of it. And you may or may not know, these are extensions of the glacier off the land. They are connected to, they are contiguous with the glacier. And they only do this if they have sufficient support or grounding point. And these can be immense. Some of them can be larger than Texas. And when they break up, they form tabular icebergs like A23A, which I mentioned and which we're going to see. So make sure you know what ice shelves are, and I'm going to come back to that. Now, when we come down to this part of this image called the West Antarctic Rift, rift implies divergent crustal motion, and it's that motion that created the Trans-Antarctic Mountains. So that's where we're going now. And this cross section across here, these are the mountains. Oops. And here are the mountains again. And this is the flat area I just showed you. And this cross section shows how depressed the crust is because of the tremendous weight of the Antarctic glacier. And so there's going to be significant rebound when everything melts. Some of these glaciers are over 12,000 feet thick. So now we come back to this flat area, which is the West Antarctic Rift, divergent motion, and one part of that goes into a subduction zone. And when it subducts, the result is or are the Trans-Antarctic Mountains shown here. So these are the product of divergent motion and subduction. Now down here, you can't see it very well, is Mount Erebus. And lo and behold, that's where we're going next. And it is an intraplate volcano like Yellowstone. Here's the plate boundary. And it is within this divergent motion I just showed you. It is a polygenetic volcano. So the base of it is a shield volcano like in Hawaii. And then it transitions into a strato or a composite volcano like Mount St. Helens, Mount Rainier. But notice this script. There's gold nose hills. The vapors give off gold, which is kind of exciting. So I did a couple calculations. It gives 80 grams of gold a day. When I did this clear back in October, gold was less than $4,000 an ounce. It's now, or at least has been, over $4,000 an ounce. I sold my gold rings, my class rings in 1972, and it was $200 an ounce. Anyway, should have held on to them. So now, in 1979, there was an Air New Zealand flyover that crashed into the slope of Mount Erebus. And this is the debris field, killing 257 people. And so if you go back to the airport, flight controllers changed the parameters, didn't convey that information to the pilots, and you had an expected path and ended up with an actual path when they got here. Because of reflections from the ice and the snow, they couldn't see the mountain and they flew into it, killing, unfortunately, 257 people. Okay, now back to the Drake Passage. And this image shows it quite well. And the current going through here is the Antarctic Circumpolar Current. It goes by two monikers. I mentioned this, the Drake Lake, which is placid, the Drake Shake, and these are three images from the Drake Shake. So let me talk about that. In 2007, this was the captain's first trip into the Antarctic. He did it at nighttime, came into the sea ice, and that was the end of their trip to the Antarctic. No one was killed, but anyway, they lost a lot of oil into the Antarctic Ocean. These are some of the waves that get kicked up. 90-foot waves are not uncommon. And this is a ship that is very similar to ours, but this in 2010, the engine conked out, so it was the end of their vacation. But our dining room was down here about at this level, and we saw waves, regular waves that came up over the dining room when we were doing the last 2 days through the Drake Passage. In the beginning, we were in the Drake Lake, and then in the last two, we were in the Drake Shake. Lots of medicine was being taken for seasickness. So the reason for talking about this, because the Drake Passage came into existence about 33 million years ago. We're going to see that when we talk about Gondwanaland. Once there was sufficient separation, then the current developed, and that acts as a belt that wraps around the continent and assists in holding in the cold temperatures. And then real recently in October, there was a major earthquake in the Drake Passage. And here's this location, just thought you might be interested. And it's said to be associated with splays with some of these fracture zones. And that's all I'm going to say about it, but it was in the news, and I thought I would mention it. So now I want to make sure everyone knows the difference between a glacier, ice shelf, sea ice, and icebergs without talking down to anyone. I'm not going to go through this. You've been taught all that, so I won't be insulting anybody. And before we go there, I want to talk the movement, and this is a term called regelation. And regelation is how ice skaters skate and how glaciers move. So the weight of a person on the skates melts the ice. You get a little bit of lubricant, and you're able to skate. And the weight of the iceberg melts the ice at the base of it, and you get water, a lubricant, and so that's regelation. If you're really interested in the physics of glacier, you can get Kurt Cuffey's book. He's the one son of my late doctoral advisor, Roger Cuffey. Be prepared for equation after equation after equation. So now I want to make sure that I've explained myself and want to make a distinction here. So floating ice shelves are simply an extension of the ice sheet because they have a grounding point. We all know what icebergs are. This is sea ice. Sea ice is an annual phenomenon, usually. Once in a while, we'll go into the second year, but normally it doesn't. And because of that, you usually don't see stratification in sea ice. When you see stratification, then you almost always have an iceberg. And sea ice can vary in thickness. It apparently is thicker in the Arctic region than it is in the Antarctic. I don't know why. I forgot to look that up. And average thickness, maximum thickness down here is around 21 feet. You can see it's not very thick here. Compare that then to tabular iceberg A23A. You can see, using this ship as a scale, how thick this is. And I told you before, it has a total thickness at this time of 1,320 feet. So those are the differences. And now we come into this, and we see all this stratification. These are the snow accumulation layers. So you know this is a glacier or an iceberg. And it just happens to be that these are in the glaciers. But it's how you make a distinction between an iceberg or glacier and sea ice. Now we come to this map, back to the ice shelves. And I told you they're huge. There's one in particular we want to talk about. This map shows the distribution of them clear around the back sides. So now we're going to go to the Thwaites ice shelf located here. Here's the peninsula, and here's the Trans-Antarctic Mountains, and Mount Erebus was over here, someplace over here. So this comes from an article in Scientific American 2019. The author was Richard Alley, who's endowed professor of geosciences at Penn State. Let me read his little comment here. The response of this gigantic glacier to human decisions will determine whether the stingrays cruising seaside streets, are sports cars or stealthy creatures with long, ominous tails. Kind of interesting. So it's also known as the Doomsday Glacier. So here we have this diagram. You can see the grounding point, and that grounding point has been severely eroded. So it's expected sooner than later that this is going to calve off. So now let's look at the map. Here's the ice shelf. Here's the Thwaites Glacier Basin, and above it is the Pine Allen Glacier. The ice shelf holds back this glacier holds back this glacier. And so if just the Thwaites Glacier and its ice shelf melt, sea level is predicted to increase 2.1 feet. May not sound like much, but that's huge. And since all three are interconnected, if all three come down, then sea level will rise from 27 feet. But let me put that in perspective. This is a small percentage of the total ice in Antarctica, and it's a small percentage of the total ice that is also in Greenland and also elsewhere around the world. And yet, just this small percentage is going to yield an predicted increase of 27 feet. That's pretty amazing. So now, in these icebergs, they carry debris, and in the sediments, you can find what are called drop stones. You may or may not have heard of these. And they can be useful in indicating stratigraphic up, which is top, or stratigraphic bottom, and this one shows the top here. I could not tell that on this. I got both these off of the internet, but here's a diagram showing they drop into the fine-grained sediments that you would expect on the ocean. So I mention those because they relate to the icebergs that we're talking about. Now we get into the different colors. And back to the question, why are the internal parts of these and the original glaciers bluish and the surface white? At the surface, you have equal, losing my thought here, excuse me, reflection of sunlight, visible sunlight, and that gives us white light. But internally, there is selective absorption. And so the longer wavelengths, which are the reds and the oranges and the yellows, they're absorbed. And you result with these shorter wavelengths, which are the blues. So now we get the green iceberg. And I told you these are rare. And it used to be thought that these are caused by having green algae incorporated into them. Well, they may contribute, but they may not. And it turns out that the parent glacier from which this iceberg was derived ground across iron and pulverized it. And iron has certain selective absorption. And that results in these greenish colors. So that's an interesting, and this is rather recent research on this. Now, here are the definitions for vergobits, should you be interested. And for this presentation, I could care less, but should you be interested, there it is. So, two rhetorical questions. This is an iceberg, not sea ice. Why? Because you can see all the stratification in it. These are the original snow accumulation lines that, of course, go through to get the oxygen isotopes, O16 and O18. But what is wrong with this image? Another rhetorical question, because the ocean doesn't tilt. I was tilted. So now we come into various shapes of icebergs. And here you can see some of the things that contribute to these shapes. These are some of the fractures in it. And up here you can see some of the original stratification. These are the bedding layers of the compaction of the snow. So you can see all these fractures. Once again, when water gets into these fractures, it breaks the ice up. So look at the stratification here, look at the fractures here, and you can see that this is certainly a discontinuity. And there's going to be calving or separation here, as there was at the top. So previous calving surface. Now, this is an iceberg. Keep in mind, when you're looking at an iceberg, you're looking at the tip of the iceberg. 1/10 of it is above, 9/10 is below. So for fun, I put the center of gravity line on. And that may be complete folly. But before I go there, look at all these discontinuities in it. They're all through it. Look down here, and there obviously was one here. The reason why this may be complete folly, because according to the 9/10 rule that I've been using, 9/10 of this iceberg is below water. I have no idea of its shape, and it could flip any way it so desires. So it might be totally useless to even put this center of gravity up there. I just did it for a conversation. So you can see more of these flat surfaces, probably due to fractures in it. We come over here and we see three small sea caves. And if you look at the first two, you can see that each of these formed along a vertical fracture. Now, I'm interested in this because when I go into a limestone cave, I know why a passage formed where it did and why speleothems are deposited where they are. And so why do sea caves form where they do? And these formed along these vertical fractures. I suspect there's one here that just doesn't show up. And, look at these flat surfaces here. All these contributed to these shapes. So there's a structural component to this. Now we come to the big green iceberg again, and we can see some of the bedding in here. Maybe this block was rotated. This looks like original bedding, but we can see that there's discontinuities in here, or there had to been, and that where there was melting and interaction with the waves to produce that. So again, structural discontinuities to come up with that shape. Now, this is A23A, and this is a tabular iceberg, and it broke off from an ice shelf. This thing is huge, or was huge, bigger than Manhattan, and weighed, this news article said 1,000 ton iceberg, and I corrected that. It's really a 1 trillion ton iceberg. And these are two images I took of it. You can see incipient sea caves forming from wave action here. And there used to be a Russian station up here, and they were doing studies on it, and then they evacuated. So that's A23A. I'll explain why it's named that shortly. Well, now that's what we're going to do. So the A and A23A, the A and 68 depends on the quadrant of the continent that it comes out of. So this is the 68th to come out of this quadrant. A23A was the 23rd. The suffix A meant that it broke off of something else previously. And I mentioned this before, South Georgia is the graveyard for most of the iceberg coming out of the northwest quadrant. That's why we saw so many in that one image. Now we're going to look at sea cave that's in rock and a sea cave that's developing at the base of the glacier at the water's edge. So let's go up here first. And we say this one is developing along a fracture. So there's structural control. Once again, when water freezes in that, it exerts a force in excess of 6 tons per square inch, quite capable of breaking the rock up. And you may ask, well, where's all the rock that broke up? And so you splash water into here and you get these mass of ice and it floats out and becomes drop stones. And then over here is the base of a glacier. You can see the forces on it with this recumbent fold. But notice there's a whole series of these fractures in it. And I don't know if these are extensions up from up above of crevasses. Anyways, they're fractures. And you can see the sea cave is being enhanced by their presence. They're certainly contributing to this. Now we come to South Georgia for a structurally disturbed section. And this is a nap or a thrust sheet. This is inferred, all inferred. We didn't get to go there. I was on a ship. I want to call your attention to the bedding up here and compare that to the bedding down here so you can see big difference. Over here, you can see the axis of this fold. You can see an axis of this fold. This is a recumbent fold. You can see two sides, A, B, and this is another recumbent fold. You can see it if you look carefully. So one is tempted to call these recumbent synclines, but I chose to say synform because you really don't know the age relationship, and these could be overturned anticlines. You really don't know, and so that's the reason I used the name synform. And then these thrust faults are inferred, but anyways, the whole thing is inferred, but I just wanted to share it with you. So some nunataks, and then some other glacial features, two horns. And here's a horn here, probably a horn here, there's a horn here. And we know that these form on mountain peaks in which there were 3 or more cirques. And so there was a cirque here, and here, like the Matterhorn in Switzerland. Over here we have a U-shaped hanging valley. Now you say, how in the world can you call that a hanging valley? This is a more typical hanging valley. It's a hanging valley because when it formed, the ocean was 300, 400 feet below that, keeping in mind this was during the Ice Age. And that's the reason I called it a hanging valley. So I rest my case. So we were floating along and I saw these intrusions. All of them are dikes by convention because there's no bedding here. And because there's no bedding, you can't tell if they're sills. And then, as I said, by convention, then they're all considered dikes. I don't know their compositions, except this one I think is dive-based, also known as dolerite. And then surrounding it is a granitic rock, possibly syenite, but anyways, some granitic rock. And you see samples of stoping here and here. This is another granitic intrusion. So we're going to take this image and go further down the shoreline, and we have more of the dive base, what I'm calling dive base. And then we have more of the whitish granitic rock, whatever that is. And we have examples of stoping. So the question is, which came first, the dive base or the granitic rock? And keeping in mind that both are intrusions. And it turns out, because of stoping, that the dive base was there first, so I give it the lower number. And then the granitic rock intruded and under great force and broke off pieces of the dive base, and that became the stoping blocks, as they're known. And then we had snow avalanches. We were around the corner when this one developed. I mean, you hear them. And fortunately, our guides were aware of this, not to take us to places where you get into these. And I suppose that if there's a lot of debris in this, these would be examples of rapid flowage mass wasting, very destructive. And you can see they can exceed speeds of 190 miles per hour. So now we get into a discussion of Gondwana land. Everybody knows that was the Southern Hemisphere supercontinent. I don't know how you can talk about Antarctica without discussing Gondwana land. And I hope I'm not talking down to anybody as I introduce 3 lines of evidence. I know it's redundant or repetitious, but I'm going to do it. And when we get to the breakup of Gondwana land at about 33 million years ago, this is seminal because this is where the Antarctic circumpolar current formed only after there was sufficient breakup and the Drake Passage formed. And as I said before, it wraps around and holds in the cold temperatures. So I apologize if you're annoyed by my 3 lines of evidence as part of the presentation. So, and there are probably 20 some lines of evidence nowadays, so I'm not going to do that. So anyways, this is Glossopteris, and it's the leaf of this gymnosperm. And here's the distribution of it. And notice that that distribution goes through the interior of these land masses. And yet today, there's sometimes as much as 1,000 miles between these land masses. How do you get a leaf that is not water soaked and still get this distribution? So, I mean, that's a conundrum. And so geologists in this Scientific American article came up with these fantastic land bridges, one here, one here, one here, for which they had 0 evidence to explain those distributions. They had no evidence of that. Anyways, obviously we know that these land bridges do not exist. That takes us to evidence number 2, which is Lytrosaurus. Here's its distribution, again through the interiors of the land masses. It's a reptile. You can see its size compared to human. It's quite small. It had no physical accoutrements. It was that could swim by. It was a poor swimmer if it swam at all. And yet, here's its distribution. How do you explain these things? And the best explanation is because these land masses were contiguous at one time. And that takes us then to paleomagnetism and seafloor spreading. And everyone is familiar with that, I understand, but it's part of the story. And we can put dates on the spreading. And if we back up, then South America and Africa keep getting closer and closer and closer together. And that then is Gondwana land. So that's the 3rd line of evidence. So, an obvious question, why is Antarctica so cold? Well, it has a Antarctic circumpolar current which holds the heat in. It has a very high albedo because of snow and ice, something like 90%. And it's a huge ice cube. It's high altitude. It's high latitude. So what does it take to reverse this? Well, you have to shut down this current, and you have to keep pumping in all those greenhouse gases that we're doing a good job of doing. So now that takes us into a little discussion of Antarctica and global warming. And here we see Permian coal. And everyone knows that coal is formed in warmer climates, so tropics and subtropics. And over here is an artist's rendition of the Cretaceous in Antarctica. And these examples are fodder for climate deniers because they say, see, we're just in one of the cycles that we had in the past, nothing more. What they conveniently don't acknowledge is that global warming today is increasing 10 times faster than the fastest rate that we know of in the geological past based upon ice cores. And here's a repository of those, and that's where we're heading. So from ice cores, we can see this graph here of carbon dioxide concentrations. Down here is a graph for 800,000 years of methane. Keep in mind that methane is much more potent and longer lasting than carbon dioxide. It just doesn't represent as great a percentage. But with the melting of permafrost, we're getting more and more methane all the time. But notice in each of these that we end up with the famous hockey stick configuration, made famous by Michael Mann, who was distinguished meteorologist at Penn State, and he's now at the University of Pennsylvania. Can you believe he got a death threat over this science? And that's the state, that's the political state that we're in with our science today, and it's just incredible. And you're also familiar with the Milankovitch cycles that predict global cycles in the past. We should be in the blue trend, which is the cooling trend, and this is the trend that we find ourselves in. And this is a lead-in to this article in Scientific American in 2011. The author is Lee Kump, who is now Dean of the College of Earth and Mineral Sciences at Penn State. It's called The Last Great Global Warming. It's a very fascinating article. And three charts in here. We're going to begin at the end of the dinosaurs. That would be in the Cretaceous at 67 million years ago. And here's the small decimal on the rate of heating based upon oxygen isotopes and other work. Then we go to the PETM, the Paleocene-Eocene thermal maximum at 56 million years ago. And notice there's a much bigger decimal. And this is the time interval in which global warming as we know it had its fastest increase. So here, look at these decimals, this decimal. Now we go to modern time and we no longer have decimals, we have whole numbers. And this is the rate that what we're seeing today. This should be alarming to everybody. I can't say it is, but it should be. And then here we have carbon dioxide concentrations for 800,000 years, temperature anomalies for 800,000 years, and methane concentration for the same time period in Antarctica. And notice these nearly perfect correlations. And here we have this tremendous spike, which is the recent tremendous spike. So now we go into next to the last part of the talk, and we're in a little bit of natural history. And this is the Magellanica penguin. I did not mention this before, and they have these stripes on. And we're going to see some more pictures of them in the Falklands where they burrow into peat bog. Into peat because it's soft and they lay their eggs and raise their chicks. Gentoo penguin, repeating what I showed you before, solid white abdomen. Solid white abdomen. And then the chin strap penguin with this interesting chin strap, and then king penguins. So a little review. Now, here are the Magellanic penguins. This is one of their burrows in the peat. Inside, there was a chick. I didn't get a picture of it. So these are the Magellanic penguins. And now the king penguins, again, you've seen these before. I'm just doing it to refresh your memory. And Gentoo penguins, this is beyond adorable. A chick here. And these are the pathways they make. And they're oblivious to people, which is unfortunate because early expedition killed and ate them. Now, if I am boring you at this point, hopefully this will open your eyes up a little bit. And this is chin strap penguins. And Amy, I don't know if I ever sent this to you, if you've checked in. And this is the world's first image of a four-wing chin strap penguin, and I took it. Of course, could be one penguin in front of the other. And that's what it was. Anyways, we had fun on the expedition in a photo contest. And I came in the final 10, and I made the professional photographer laugh. So anyways, that's the four-wing chin strap penguin. And these are the pathways they make going up to the rookery at the top. Look how worn they are. And I mean, you can just see they're smooth from many, many trips up and down. And here you can see a bevy of them. And there's always a sucker. There has to be someone. Every long journey begins with the first step, and someone has to go in because they have to feed, and they're concerned because of leopard seals, which kill them. And so that's the reason for the little title, Who Will Be First? And once one goes in, then the other ones go in. And here are the pathways they make. You can see how close they are in some instances to the people. They just ignore you and continue on their trek upward. And then this is a rookery back here, but you can see more of the penguins. This is what you see. So really fascinating. And then these are more of the fur seal. Sorry for this. Fur seal pups. And this is a small pup. And we were told to stay, I can't remember, it's 20 feet away from the wildlife. And I was at Stromness, which again is on South Georgia. And I'm standing there, and right at my feet is this little fur seal pup, cute as anything. I backed away, and I'm going to be talking to you about a situation later on South Georgia, so I'll hold off on that. So here's the skua that I mentioned before. This is a skua, and this is the southern giant petrel we saw. These two are pesky birds. They fly into the rookeries and peck the eyes out of the penguin chicks. This is the albatross. It has the largest wingspan of any bird in the world. Sometimes they never go on land for more than a year. They are so efficient in flying and then landing in the ocean. Just an amazing bird. And then just some more birds. I won't talk about those in details. I wanted to show you some images of them. So an abundance of birds there. Now back to these. These are the elephant seals. And again, I wanted to stress these are behemoths. And here are two that are sizing off on each other. And then the leopard seal. And here we come up with a story. So cute as it may be, there's a story to this. And when we get to the end, which is coming up soon, and the Shackleton expedition, when they were on an ice floe, one of the expedition members was going across the ice and encountered a leopard seal. Keep in mind, these things can be 11.5 feet in length and weigh up to 1,320 pounds. And fortunately, it went under the ice, but the ice was thin, and it traced that person to the other side, came up and attacked. But another member of the expedition was there with a rifle, shot it, so they had blubber for their blubber stoves and meat that they ate. But that's the story of this. And they can move 5 miles per hour on land, and you, as a expedition member, are wearing heavy boots and heavy clothing. That would be challenging. So, a question, why are there no polar bears in Antarctica? Because when they evolved, they would have to go down through the tropics. Can you imagine a polar bear going through 90-degree temperatures, which some of them are off the coast of Florida, or going on land through the tropics? I don't think they could do that. And this, I just mentioned, I'm not going to read any of this to you. I came to a website and was asked a question. I wanted to see what people would say. I already knew the answer. Why polar bears don't live there? And they gave all this information and never answered the question. Can you believe that? So if you're talking about the marine environment in Antarctica, this is what sustains it. And these are known as krill. You heard of krill oil. Well, it comes from the krill. And we're going to see that baleen wells, such as humpback whales, then filter these out by huge amounts. And so that's the krill. And they are up to about 2 inches in dimension. So now we come to the end of the talk. And two of them were simultaneous. Amundsen from Norway and Scott from Great Britain. Amundsen beat Scott's expedition by about a month. Everyone on Amundsen's expedition lived. Everyone in Scott's expedition died. And the British have a great way to glorify deaths. And they died by starvation, they died by exposure, and one person walked out to commit suicide. And they glorify this. Oh, well, whatever. I can't see it. I mean, it's a horrible way to die. So now we come into the end of the talk, and this is a discussion on the Imperial Trans-Antarctic Expedition 1914-1917. So the South Pole had already been visited. So Ernst Shackleton, shown here, was the leader, and his goal was to cross from one part of Antarctica to the other part. But that never made that attempt because their ship, shown here, the Endurance, got trapped in sea ice. They came from South Georgia down and got trapped in sea ice. And here you can see the sea ice is not that thick, but anyways, eventually the pressure of the sea ice crushed it, and they go into the lifeboats, and they floated, and then eventually, or they didn't go in lifeboats, they floated on sea ice. And they did that for about 4 months. And the sea ice has this proclivity to break up. And below you is the Antarctic Ocean. So then they resorted to lifeboats. And they had 3 lifeboats, the largest of which was 23 feet. They had 28 people in 3 lifeboats with all their equipment and food. And they sailed for about a month, and they were desperate. They had no fresh water for something like 48 hours. And one guy had gangrene so bad they had to get him ashore to amputate the toes. And so they went to Elephant Island. No ships go to Elephant Island. They would never have been rescued there. And so it was at Elephant Island that Shackleton and 5 others took the lifeboat called the James Caird. And here they are sailing off to go to South Georgia. It's now you see a connection between South Georgia and this expedition. And so by the time they crossed the Drake Passage, they had encountered 90-foot waves, their rudder was torn off, and their sails were tattered. They had little or no control over their boat, and they went into King Haakon Bay, if you recall, here it is, that name, And they made this very daring, three of them, Shackleton and two others, and crossing over alpine topography nonstop. They didn't even take sleeping bags. And it was this trek. I mean, look at this topography. They're crossing crevasses, they're crossing glaciers, and they did this nonstop. And they came down. And when you're standing in Stromness at the abandoned whaling stations, it can almost grip you. You can look up and see the very ridge where Shackleton and the two others came down for rescue. And that's just an amazing story. So I would tell you that if this is interesting to you, read the book called Endurance. It is gripping, gripping, gripping. Fantastic story. And my last slide for the talk tonight is an article I published because when they were crossing the Drake Passage, they had to use celestial navigation. They didn't have radio. They didn't have GPS. And it's the same technique that I taught my high school earth science students, and I was kind of proud of that. So thinking of that, these students were on a par with the early navigators. And having said that, I thank you so much, and we come to the end.
Thank you, Charlie. That was a whirlwind. Very nice.
Oh, so everyone heard it, I hope.
Yeah, you were muted the whole time. Can you repeat it? No, we're all good. So we're going to do something a little different this time for Q&A. I think anyone who would like to ask Charlie a question, you can unmute and ask your question. If not, you can, if you don't have a microphone, you can put it in the chat and we'll read it. All right, Charlie, you're getting some praise, but no questions yet. I don't know if you can see the chat.
Yeah, there may be no questions. That's okay.
I don't have a question. It's Kent Littlefield. Thanks a lot, Charlie.
Yes.
I read Endurance, and I guess the only thing you didn't mention, which was miraculous to me, was that everyone survived that ordeal, which was over a year of being in cold and wet and having to navigate across to St. George's Island in those lifeboats.
And
not everyone went across, but when they finally got rescued.
Yeah. You're absolutely right. Can you hear me?
Yes.
Oh, okay. Yeah, I forgot that. And that was the whole point of going to Stromness, because the whaling station, there were people and ships for rescue. And indeed, they came back to King Haakon Bay, rescued those, went down to Elephant Island and rescued them. And I thank you, because that slipped my mind. And that was
amazing, really, because when I first started, I only expected the worst. When I started reading, I was like, oh no, another one of those.
Yes.
Thanks a lot.
Thank you.
Hey, Charlie, Fred asked, did you see any icebergs flip while you were there?
No. And, we were floating between them. And if you think about it, that could be dangerous because they can flip suddenly.
Hmm.
And in retrospect, I thought about that. But anyways, fortunately, it didn't happen. And there is a sport out called glacier surfing. And people go up to these places where the glaciers calve off, and that generates a small tsunami. And they actually surf this in this cold weather. Obviously, they have wetsuits on, but there's a sport out called glacier surfing.
Wow.
And that's a result of that. But I had thought about that afterwards, and these are big. Some of these are big icebergs.
Yeah. Well, wonderful. You're getting more praise in the chat. Is there anyone have any more questions? We're just slightly over time. Perfect. Oh, wait a minute. We got a question. With the Panama Canal having issues with cargo ships becoming more common. Okay. With the Panama Canal having issues, are cargo ships becoming more common? That's the question.
I'm not sure. Maybe you can help me on the question. What they're asking if cargo ships are going.
Are
I don't know
becoming
how
more common
does that
in the
relate to
Antarctic.
Antarctica. I don't know how that relates to Antarctica.
But it's cargo ships now coming around through
Oh, through the
near
Drake
Antarctica.
Passage. Through the Drake Passage.
Yeah.
I don't know. I don't know. All I can say is it's torture on ships going there because of the Drake Shake, and they can pick their time. But and the I didn't mention this, or maybe I did, but when the people were sailing, when Shackleton and the others were sailing, they encountered 90-foot waves in the Drake Passage.
Wow. A question came in, and this is a question I wanted to ask you. Did you take all of these photos in the
Yes.
presentation?
Yes.
Phenomenal. Yeah, they were really nice.
Well, I had so many more, but in the essence of time, you can't show them. And I was just blown away. This, to me, of the many travels I've done, this was so special. And if anyone has an inkling of going there, please do that. I mean, this will affect your life.
Wow, that's great.
Yeah. Now,
Well,
I want to offer an apology. I hope it didn't talk down to anybody on my explanations.
no, I thought it was perfect. Yeah, I want to thank you for your time, and I'm glad we were able to get the technical issues worked out because this is phenomenal.
Well, I want to thank you for your persistence. Yeah. And I want to thank everybody for attending.
Yeah, very nice. That was wonderful. And for those of you, everyone online, like you're going to get your certifications. I'll send that out over the weekend, so we're all good. And next month, as we mentioned, committee meetings before the meeting, and then our topic for discussion next month is AI and the geoscientists and this geoscientists. So so we look forward to that. And thanks again to Charlie. And I want everyone to have a good evening.
Thank you, Al.